Hello, welcome to the class on Advanced Electromagnetic Theory and Antennas. I am Professor Rakesh Singh Chaturme. In this class, we'll discuss about the open-ended waveguide. First, we'll consider the open-ended rectangular waveguide. This figure shows a open-ended rectangular waveguide. The dimension along the x-axis is A, along the y-axis is B. Usually A is greater than B. As you already know that for the rectangular waveguide, the dominant mode is TE10 mode. And you know the fill expression for TE10 mode. In the TE10 mode, the fill will have only y component, and variation of the fill will be with respect to x. So it has a cosine function like this: maximum at the center and 0 at the edges. Here fill will be 0, here fill will be 0. You'll have maximum fill at the center of the waveguide. So the fill can be expressed as a cosine function for a rectangular waveguide. So we can find out the aperture fill now. Aperture fill will have only y component, and it will be E0 cosine of pi x just by A. A is this dimension, and fill is directed along the y-axis, and fill will have this expression in this open-ended aperture of the waveguide, and at other places it will become 0. So this is the expression for the aperture fill for open-ended waveguide: E0 cosine of pi x just by A, directed along the y-axis, and outside this aperture fills is always 0. So we have the aperture fill. So the aperture antennas, the analysis are three-step process. First, stabilize the fills and the aperture, then you find the 2D Fourier transform of the aperture fill, then you use the equation 24.1 and 24.2 to find the fills. So second step is find the 2D Fourier transform of the aperture fill, and this is the expression for the 2D Fourier transform. In this case, our fill has only y component, and it was expressed as E0 cosine of pi x just by A. So we can combine this exponential j beta x just and do the integration, and we can also do the integration for exponential j beta y just, and this is from minus b by 2 to plus b by 2. This is from minus a by 2 to plus a by 2. So this 2D Fourier transform was for minus infinity to plus infinity, minus infinity to plus infinity, but our fill is confined between minus a to plus a by 2, minus b by 2 to plus b by 2. So the integration will be from minus a by 2 to plus a by 2, minus b by 2 to plus b by 2. You already know what is the integration for this kind of function. This is exponential function. It will give you exponential function. So integration of this will be exponential j beta y just divided by j beta y. And you plug in the limits here, minus b by 2 to plus b by 2. So finally is the expression you have here, and this expression now you can express it in the form of sine function by multiplying 2 here, 2 here. So this looks like exponential j beta y b by 2 minus exponential minus j beta y b by 2 divided by 2j, which is sine of beta y b by 2. And further we can make it as a sinc function by expressing it in this form. You multiply by b in the numerator and multiply by b in the denominator. Then finally you can express this as sine of beta y b by 2 divided by beta y b by 2. This is a sinc function. So final expression for this integration you have here will be b sinc of beta y b by 2. How about this integration? This integration also you can do it. How you can do it? You express this cosine function as in terms of exponential function. Then the integration for exponential function is very simple. So when you integrate exponential function, you get exponential function. You can put the limits. Then finally the answer would be 2 pi a cosine of beta x by 2 divided by pi square minus beta x whole square. So we have the 2D Fourier transform of the aperture fill. Now it's multiplication of this function and this function here. So we have the 2D Fourier transform of the aperture fill, which is basically multiplication of the two functions we have derived. So finally the expression is 2 pi ab e naught sinc of beta by by 2 cosine of beta x by 2 divided by pi square minus beta x a whole square. So now this is the second step. First step is stabilize the fields in the aperture, and once you have that, you do the 2D Fourier transform of the aperture fields. Then after that you use equation 24.1 and 24.2 to get the fields in the far field of the antenna. So the expression you will have now would be simply this one, because all other terms are 0, so you have only this component of the electric field. So this is the Fourier transform of the aperture field, which has only y component, and this will give you the electric field in the far field theta component. This will give you electric field in the far field phi component. Two term is from the method of images. We have already discussed that. So let us plug in this expression you have derived for the 2D Fourier transform of the aperture field in the expression for the electric field in the far field theta and phi component. You can find out. And we want all the fields in terms of theta and phi. So what is beta y? What is beta x? Beta x is simply beta sine theta cos phi. Beta y is beta sine theta sine phi. So beta x is the projection of beta vector along the x-axis. Beta y is the projection of beta vector along the y-axis. So we are interested always in two principal plane. One is E plane, another is the H plane. So here your field, aperture field, was directed along the y-axis, so we'll have maximum field of the radiated field along the y-axis. So the E plane would be yz plane. So in the yz plane, pi becomes pi by 2. You put that, beta x will become 0, beta y will become beta sine theta. So you have the electric field in the far field, which is simply a sinc function, and electric field in the far field theta component is non-zero but phi component 0. That is because phi is pi by 2. So look at this expression here. When pi becomes pi by 2, this becomes 0, everything becomes 0. But this one, sine of pi by 2 is 1, so this term exists. So the expression for the electric field in the far field for the E plane will have only theta component, and it is actually dependent on this sinc function here. So you have a sinc function. Obviously sinc function main lobe will be at this argument is equal to 0, and the side lobe will be minus 13.2 dB down. We have already discussed that in the previous class. Side lobe level for sinc function is minus 13.2 dB. For the H plane, phi will become 0. It's the xz plane, and pi is 0 for the xz plane. Beta x will become beta sine theta, and beta y will become 0. So you can find out the electric field in the far field for the H plane when phi becomes 0. When phi becomes 0, you can look at this expression. When phi becomes 0, this term will become 0. That means electric field will not have any theta component, but this term will become, cos of phi will become 1. So electric field will have phi component. So the H plane will have only phi component, it will not have any theta component, and you can see the expression for the electric field in the far field, phi component would be expressed like this. Look at this, you have the term cosine of theta. Because of this, you will see later on that radiation pattern, when you draw it for the H plane, it will be mostly decided by this cosine theta. It will have a cosine variation. So let us look at the electric field E plane and H plane of the open-ended X-band waveguide. We have plotted this electric field E plane and H plane at 10 gears. You can plot it for any other frequency also. The only thing is that dominant mode should be propagating at that frequency. This is for the X-band waveguide. X-band waveguide has A is equal to 22.86 millimeter, B is equal to 10.16 millimeter. That's a standard waveguide. We use such kind of waveguide in our microwave experiment in our lab also. So at 10 gears, the radiation pattern E plane and H plane looks like this. H plane, as I already told you, it's decided by this cosine theta here. So you can see that the H plane field variation is almost following like cosine theta. So cosine theta, theta is equal to 0, you have maximum. Then theta is equal to pi by 2, you have minimum. So this looks like a cosine function. These other terms will also contribute, but major contribution will be from the cosine theta here. And you can also see the E-plane radiation pattern. E-plane radiation pattern is a sinc function. So you have maximum at 0, then this is a Manlov. So you can see that radiation pattern of the open-ended X-band waveguide at 10 gears is very broad. It's not narrow. It's very broad. E-plane is very broad. So later on we'll try to improve this beam, main beam, to have more and more narrower beam, so that it can have a pencil beam by realizing something called horn antenna later on. Because of this very broad beam, gain of this kind of antenna, which is open-ended waveguide, is not good. So we need to make some modification in the design so that gain should be improved, beam should be more narrower and narrower. That is actually the outcome of what is called horn antenna. That's a topic of discussion of the next class. Anyway, so let's go to the next topic we are discussing here. We can also find the directivity of this open-ended waveguide. That's the usual formula. You have 4 pi by lambda square. You do integration of the aperture electric field, take square of that, and you divide by, you also do the integration of the square of the aperture electric field. So we can do that. We can do this, a simple derivation you have here. You can derive it, and finally what you get is, the answer is, after making all this calculation, the final answer is 4 pi by lambda square 8ab by pi square. So this 4 pi by lambda square into ab, what is 8 by pi square? What is 8 by pi square? See, basically if your aperture was very efficient, no, then it should be simply 4 pi by lambda square into a into b. A into b is the area of the rectangular aperture. But now, since this is open-ended waveguide, aperture efficiency is not good. Because of that, we have a term 8 by pi square, and it is actually 8 by pi square. If you calculate it, it's 8.81. So people usually say that open-ended rectangular waveguide has aperture efficiency of 81%. Because of that, we have a extra term here, 0.81. If efficiency was 100%, it should have been 4 pi by lambda square a into b. A is the area. A into b is the area of the aperture. So one major observation we have observed for such kind of antenna is that directivity is not very good, and beam was very broad. So you need to flare out the waveguide and create horn antenna so that directivity becomes higher and higher, and the bill becomes more narrower. We will have pencil beam. Okay, just before that, let's discuss about open-ended circular waveguide. Similar to open-ended rectangular waveguide, we can also find the aperture field for open-ended circular waveguide, and you know that dominant mode for open-ended waveguide, circular waveguide, is TE11 mode, and you also know the fields for the TE11 mode, and this is actually discussed in any undergraduate courses, microwave engineering courses. You can always find out the fields for the rectangular waveguide and circular waveguide by solving the wave equation. And we assume that in this class you already know all these expressions. So the aperture field for the dominant TE11 mode will have rho component and phi component, and it is non-zero for rho dash is less than or equal to a. So that means inside the circular cross section of the open-ended circular waveguide, the field is non-zero. Outside that, all fields are zero, just like you have done for the rectangular waveguide. So aperture field will have rho component and phi component. Rho component is simply E0 J1 1.841 rho dash by a sine phi dash by rho dash. So basically, you solve the wave equation for circular waveguide in cylindrical coordinates, and when you solve it, your solution will be in terms of Bessel's function. So the rho component of the electric field will be actually mainly contributed by the Bessel's functions. These are Bessel's functions of first kind of order 1. And by now you already know what are Bessel's functions. We did a lot of discussion on this when we discussed about the cylindrical waves. So the major contribution rho component of the electric field will be from the Bessel's function of first kind, 0 order. You also have sine phi dash divided by rho dash also. Similarly, phi component would be actually major contribution would be derivative of the Bessel's function of first kind, first order with respect to rho dash, cosine of phi dash. And what are these? Why do I have a term here 1.841? It's basically we denote this kind of term here. This term here is basically psi x psi 11 dash. What is this notation here? Notation here P and M dash. When you do the waveguide analysis, circular waveguide analysis, you will find out what are this P and M dash. What is P and M dash? Is basically mth root of the derivative of the Bessel function. So mth root of the derivative of Bessel's function. So you take the derivative of the Bessel's function, find out the mth root, and what is n here? N is the order of Bessel's function. So you take the derivative of the nth order Bessel's function, find the mth root, that would be P and M dash. So psi 11 dash means you are taking the derivative of the first order Bessel's function of first kind and you are finding the first root of that. And this is a standard value you have for the first root of the derivative of the first order Bessel's function of first kind is basically 1.841. And this is the smallest root, that's why it has the dominant mode as D11 mode. These roots will decide what kind of modes will be propagating inside the waveguide, and for the dominant mode the root we are considering is psi 11 dash and it is 1.841. This is the smallest value, that's why it will have the lowest cutoff frequency inside the waveguide. Okay, so let us denote this del by del rho dash of J1 1.841 rho dash by A as J1 dash. It's a compact notation. Instead of writing del by del rho, I will just replace it by J1 dash 1.841 rho dash by A in the following slides. So now we have established the fields inside the aperture of the circular open-ended waveguide. So next thing is we have to find the Fourier transform of the aperture fields. But in the expression you have for the electric field in the far field of the aperture antennas, the equation 24.1 and 24.2, we want the Fourier transform of the aperture field, which is EAX and EAY, X and Y component of the aperture electric field. We have derived like that. So now, but the aperture fields we have here is rho and phi components, but we are not interested in rho and phi component, but we are interested in EAX and EAY, so that I can plug in those values of the Fourier transform of EAX and EAY in 24.1 and 24.2 to find the far fields of the aperture antenna. So that is very simple. So you already have the expression for the EA rho, EA phi, EAZ is anyway 0. So you do the coordinate transformation and find out EAX and EAY, EAZ is anyway 0. So this is the coordinate transformation matrix for transforming from the cylindrical to Cartesian coordinates. Cosine of phi dash minus sine of phi dash 0, sine of phi dash, cos of phi dash 0, 0, 0, 1. We have a prime coordinate here dash here because this aperture field is the source for the radiations we are considering for the aperture antenna. So now when you do the coordinate transformation, EX will have terms like this. First term is J1 and second term is J1 dash, and this is contribution from rho and phi component for the EAX. Similarly here also for the EAY, you will have contribution from the rho and phi component. You will have J1 here, J1 dash here. One point to be noted is that you also have sine of 2 phi dash here, sine of 2 phi dash here after doing the coordinate transformation, and you also have sine square phi dash, cos square phi dash here. So now we can take the Fourier transform of this EAX and EAY. When we take the Fourier transform, sine of 2 phi dash can be expressed in terms of exponential function by using Euler's theorem. That's why I have pointed out that we have a sine of 2 pi dash here. here also, sine square phi dash, cos square phi dash here. So let us try to find the 2D Fourier transform of the aperture field. And for the Ex component, let us try to find, so you do the integration. So now we are in the cylindrical coordinate system. The area element for the aperture is in the shape of a circle. So inside the circle you take any source point, any source element, array element could be expressed as rho dash d rho dash d phi dash. So rho will be from 0 to a and phi will be from 0 to 2 pi, and this is the expression of the EAY we have. And EAY expression was like this: you have sine 2 pi dash here, then this is J1 here, this J1 dash here. And 2D Fourier transform also, now we are in the spherical coordinate system, or for that this expression, no, this expression for the 2D Fourier transform, you need to multiply by this to the EAY and you integrate it over d phi dash rho dash d rho dash, then you will get a 2D Fourier transform. We have done this when we consider the circular aperture, uniform circular aperture. 2D Fourier transform is expressed like this: exponential j beta rho dash sine phi cos of phi minus phi dash. We have done derivation for that when we consider uniform circular aperture also. So now you need to do the Fourier transform of this expression you have here, which is the EAY. And as I already told you, you have a sine 2 phi dash here. You can use Euler's expression, Euler's theorem and the Euler's formula, and you can find out sine 2 phi dash is simply exponential 2j phi dash minus exponential minus 2j phi dash divided by 2j. Okay. So we are considering the integration of this over phi dash. We'll do that integration first and we'll do this integration later on. So this integration, I will call it I1. We are doing integration from 0 to 2 pi sine of 2 phi dash exponential j beta rho dash sine theta cos phi minus phi dash d phi dash. This you express in exponential term. Now you can easily do the integration now by putting a new variable phi dash minus phi is equal to zeta. So d phi dash will become d zeta. So I1 can be expressed now in the form minus phi to 2 pi minus phi. Since we have changed the variable, this limit will also change. Minus phi to 2 pi minus phi there. Minus phi to 2 pi minus phi exponential j beta rho sine theta cosine of zeta plus j 2 zeta d zeta. And you can take out this outside. This is the exponential term, exponential 2j phi by 2j. We have exponential term here. After we substitute phi dash minus phi is equal to zeta, then phi dash will become phi plus zeta. That's why we have exponential 2j phi here. When we replace this phi dash by zeta plus phi, we'll have extra term here, exponential 2j phi by 2j. Similarly, we'll also have extra term here, exponential minus 2j phi by 2j. Limits, same limit you have here. Exponential term is also same except for this sign change here. We'll have plus sign here, we'll have minus sign here. Why? Because we are replacing phi dash as phi plus zeta, and here we have a minus sign here. Because of that, there will be a sign change here. So now we can use Bessel's identity. If I want to do integration 0 to 2 pi exponential jx cosine of psi exponential jn psi d psi, then the integration is, this is a Bessel's identity, 2 pi j to the power n jnx. Jnx is the Bessel's function of nth order. So now look at this expression you have here. N is either, what is n? N is this term here. N is either plus 2 or minus 2. What is x? X is beta rho dash sine phi. Psi is zeta. So when we compare this identity and this equation, what we are getting is n is either plus minus 2, x is beta rho dash sine phi, psi is zeta. So we can directly apply this identity. And now the integration 1 will become minus exponential j2 pi by 2j 2 pi j to the power n is 2 here, so it will become minus here, minus 1, j to the power 2 is minus 1, j square is minus 1, so you have minus sign here, exponential j2 pi by 2j 2 pi, n is 2, so j2, what is x? X is beta rho there sine theta. And similarly you can also do it here, n becomes minus 2 now, n becomes minus 2, so 2 pi j to the power minus 2 will become j to the power minus 2 will become plus 1. Then you have jn is what? J to the power minus 2 will become minus 1, and this minus and minus will become plus. So this become plus, because 1 by j square is 1 by minus 1. So minus 1 by minus 1 is minus 1, but we have a minus sign also here. This minus and minus will become plus. Exponential j2 pi divided by 2j, 2 pi, n is minus 2, j minus 2 beta rho there sine theta. Here again we can use another Bessel identity. J minus nz is equal to minus 1 to the power n j nz. What is n now? N is 2. So minus 1 to the power 2 is 1. So j minus 2 and j minus 2z should be equal to j2z. So this term and this term is same. So you can sum it up. Finally what you get is I1 is minus 2 pi sine 2 pi j2 beta rho there sine theta. So when you sum it up, see, these are common term here, this and these are same, 2 pi j2 beta rho there sine theta. What is this term here? Exponential j2 pi minus exponential j2 pi divided by 2j plus exponential minus 2j pi divided by 2j, that is minus sine of 2 pi. So finally I1 is very compact. We have minus 2 pi sine of 2 pi j2 beta rho there sine theta. So we have done the integration 1. We can also do the remaining integration to find the 2D Fourier transform of EAX. So minus E0 pi sine of 2 pi j2 beta rho there sine theta. That's what the integration I1 was. What was the remaining term? Remaining terms were dependent on rho dash, and we do integration over d rho dash, and rho is going from 0 to a. So again here we can use the Bessel identity for this term. When I do the integration of this term, I can use this identity alpha jp plus 1 alpha x is equal to p by x jp alpha x minus del by del x of jp alpha x. P is the order of the Bessel's function. J means it's the first kind, Bessel's order of first kind. X is the variable, alpha is a constant. So look at this expression, you compare these two equations. What you can observe is that, let us look at the right hand side. Right hand side, when we compare this J1 and JP, that means P is 1, alpha x, x is rho dash is a variable, x is a variable, constant alpha is 1.841 by a. So alpha is 1.841 by a, x is rho dash which is a variable running, p is equal to 1. In that case we have Fourier transform of EAX theta phi. This whole term can be replaced by this. Again you can compare this also. This looks like del by del x of JP. P is 1, so J1 dash alpha x, alpha is 1.84 by a, rho dash is x. So this term and this term all are same, so we can just plug in this expression like this here. What is alpha? Alpha is 1.841 by a, JP1, P is 1, so J2. Alpha is what? 1.841 divided by a, rho dash is x. So this term here inside the second bracket multiply with this will be equal to this term here when you after you do the integration, without doing integration also. This doesn't have any integration. I am just expressing this expression in a more compact form like this. These two terms can be replaced by this one term here, and In our case, alpha is 1.841 by A and P is 1, so J2 alpha is 1.841 by A, X is rho dash. So we have a more compact expression of these two terms replaced by one term, which is Bessel's function of first kind of second order. Now you can do the integration. Here also I will use another identity when I do integration of x jn alpha x jn gamma x dx. It's equal to gamma x jn alpha x jn minus 1 gamma x minus alpha x jn minus 1 alpha x jn gamma x divided by alpha square minus gamma square. So jn alpha x and jn gamma x. So n is 2 now. Here also n is 2. Alpha x, alpha is what? Alpha is beta sine theta, x is rho. Gamma is 1.841 by A, x is rho there. So we are doing integration of this term and this term. Alpha is beta sine theta, x is rho there, gamma is 1.841 by A, n is 2. So plug it in this identity, alpha, x, gamma and n is equal to 2, then you will get the integration now. When we do that, the integration turns out to be like this: 1.841 j2 beta h sin theta j1 1.841 minus beta h sin theta j1 beta h sin theta j2 1.841 divided by beta sin square theta, beta is sin theta square minus 1.841 by A whole square. So we have used this identity to get this result here. So we can further simplify this expression. Anyway, this topic on the aperture antenna is highly mathematical. I'm trying to simplify it, explain each and every step so that you understand what's going on. We can use the Bessel identity 1. I will call this as Bessel identity 1. This identity here, but with a simplification, alpha is equal to 1. So in that case, alpha is 1. So jp plus 1 x is equal to p by x jpx minus del by del x of jpx. So this is another identity you can get from Bessel identity 1 by putting alpha is equal to 1. So, and you can take x is equal to 1.841, that is psi 11 dash, p is equal to 1. In that case, what happens to this equation here? X is 1.841, so p is 1, so j2 1.841. P by x. What is p? P is 1. What is x? X is 1.841. So jp is j1 1.841 by 1.841. This is j1 dash of x is 1.841. And you, at the starting of this topic on the open-ended circular waveguide, we know that first derivative of the Bessel's function has root equal to 1.841. What was 1.841? It was the first root of the first derivative of the Bessel's function. So that means j1 dash 1.841, since 1.841 is the first root of the derivative of the Bessel's function, this term will become 0. So j2 1.841 will become j1 1.841 by 1.841. So j1 1.841 can be expressed as 1.841 j2 1.841. So I want to replace this j1 term here so that I can take common j2. So here I want to take j2 common so that I can get rid of the j1. So similarly, what you can write now is so I have taken out the common j2 1.841. So here I have j2 1.841, but here I have j1 1.841. So I will replace this by j2 1.841 into 1.841. Then I can take out j2 1.841 common from these two terms. And you can simplify the previous expression. The final expression would be minus a square j2 1.841 divided by 1.841. And we have taken 1.841 common from the denominator also. and final expression is 1.841 square j2 beta a sin theta minus beta a sin theta j1 beta a sin theta divided by 1 minus beta a sin theta divided by 1.841 whole square. So this is the final expression you have for the integration. So we can write down the expression for the 2D Fourier transform of the EAX component. It's a very long expression you have here. E0 2 pi a sin phi cos phi, that was sin 2 theta term, you can express now as 2 sin theta cos theta, j1 1.841 divided by 1.841 square. This is a contribution from the first. See, you have this here, this term here, sine of 2 pi. No? So the final expression is like this. We have derived this now. Similarly, you can also write the expression for EAY term. EAY term can be similarly derived, and you can find it on your own, or you can refer to Balani's book. So E0 2 pi a j1 1.841 divided by 1.841 square, and this long expression you have here. So this is the EX for a transform, EAY for a transform. So now you use equation 24.1 and 24.2 to find the far fields of the open-ended circular waveguide. Two multiplication factor is from the method of images. This is the usual expression you have for the electric field in the far field of the aperture antenna, theta and phi component. So you can simplify this EAY Fourier transform of EAY component sin phi plus Fourier transform of EAX component cosine of phi. You can find it out, and it turns out to be very simple. E0 2 pi a j1 1.841 sin phi j1 beta a sin theta by beta a sin theta. Similarly, you can also find out EAY Fourier transform cosine of theta cos of phi minus EAX for a transform of that cos of theta sin phi is simply E0 2 pi a j1 1.841 cosine of theta cos of phi j1 dash beta a sin theta divided by 1 minus beta a sin theta divided by 1.841 square of that. So this is the expression. So now you can plug it in. This term here is this term here is this. You can plug it in. You will find the electric field in the far field theta and phi component of the circular waveguide. So this is the final expression you have for the electric field in the far field of the open-ended circular waveguide, theta component and phi component. We can find out the E-plane and H-plane for this open-ended circular waveguide. So now let us assume that E-plane is YZ plane, phi is equal to pi by 2 at YZ plane. In that case, you put phi is equal to pi by 2, this term will become 0, this term will become 0. This one term will become 1 and this term will become 0. We'll have only theta component, this expression. And you can see that the main contribution in the radiation pattern for the E-plane of the aperture antenna, which is the open-ended circular waveguide, is Bessel's function J1 with the argument beta a sin theta, phi component 0. So you can find out the 3 dB pattern point in the E-plane for phi is equal to pi by 2 or YZ plane, E-plane. That means when the electric field has been reduced by 1 by root 2 from the maximum value. 3 dB point means power has been reduced by half, but the electric field will be reduced by 1 by root 2. So this is the main contributing term here. So this beta a sin theta 1 should be equal to 1.6162 for the 3 dB pattern point. Then you can simplify sin theta 1. Sin theta 1 can be expressed as 0.5145 lambda by d. Lambda is the wave length, d is the diameter of the circular waveguide. Similarly, you can also find out half power beamwidth E-plane. So from there, you can find out the half power beamwidth for the E-plane would be twice of this theta 1. So theta 1 is sine inverse of 0.5145 lambda by d radian. You can even change this to degrees, it will become 114.59 sine inverse 0.5145 lambda by d in terms of degrees. D is the diameter, lambda is the wavelength. So it means when you keep on increasing the diameter of the circular waveguide, open-ended waveguide, this half power beamwidth is going to reduce. Similarly, you can also find out the side lobe level. The side lobe level you can find out because this is a Bessel's function, and you can cross check, it's minus 13.62 dB. And we can also find out beamwidth between the first nulls. For that you need to find out the first zero or null point, and you know that in the E plane the major contribution is from the Bessel's function of first kind J1 beta h sin theta. This should be equal to 0 for the null. So J1 beta h sin theta should be equal to 0, and you can find out for that value of beta h sin theta null should be equal to 3.8137. So beamwidth between first two null will be twice of this theta null. Theta null you can find out as sine inverse of this divided by this. So it becomes to sine of 1.2197 lambda by d in terms of radian. In terms of degree, it turns out to be 114.592 sine inverse 1.2197 lambda by d in terms of degrees. You can also find out the directivity of such kind of open-ended circular waveguide, and aperture efficiency turns out to be, in this case, is 0.836. Like last time it was 0.81. For the rectangular waveguide, aperture efficiency was 0.81, but for the circular waveguide it has a little bit higher aperture efficiency, it's 0.836. So you can find directivity as aperture efficiency, which is 0.836 for the circular open-ended waveguide. For pi by lambda square, area of the aperture is pi a square. You can express this also 0.836 times to pi a by lambda whole square. You can also plot the E plane and H plane of the open-ended circular waveguide. This I have done using, I have written a small MATLAB program, and I have found out the E plane and H plane radiation pattern of a open-ended circular waveguide at 15 gears. I have taken the radius of the waveguide as 5 centimeter. This is the E plane radiation pattern, and this is the H plane radiation pattern. You can see that E plane radiation pattern is dependent on this Bessel's function of first kind J1 beta s sin theta. You can easily plot it in MATLAB. Bessel's functions can be plotted as J1b, Bessel G. Bessel J1 will give you Bessel's function of first kind of order 1. You can plot it. This is the E plane, and the H plane is basically, as I told you, this cosine theta would be the dominant term. So you have a cosine function like this, maximum at theta is equal to 0 and minimum at theta is equal to pi by 2. And this term also you need to include it while you plot it. This J1 dash beta h sin theta, J1 dash can be plotted easily in MATLAB. You can find it out. And what you can observe is that the beams are more narrower than that of the E plane and H plane radiation pattern of the rectangular waveguide. You can see that, you see the value here. These values are very small. It's going from 0 to 0.35. But for the rectangular waveguide, it was going up to 0.8. So beams are more narrower. So, and the directivity is also slightly higher. You can see aperture efficiency is 0.836 now. For the rectangular waveguide, it was 0.81. And directivity is slightly higher. Beam is more narrower. But this is not good enough. Still the directivity is quite small and the beam is very broad. So basically you need to modify this to a horn antenna so that you'll have better directivity and pencil like beams. So that's a subject of discussion for the next class. Thanks for your attention.